Welcome friends. So in the last two sessions we have studied distribution systems with its brief introduction, comparison between its transmission network and distribution network, and we have seen few problems on distribution network with DC excitation, with single end feeding configuration as well as double end feeding configuration. Now in this section or in this phase of study we shall see the uniform loading. Okay, we shall see the uniform loading. So let us, this is a feeder, it is a scheme, it is feeding at one end, let us say this voltage is V. So now along the length of this feeder, if the total length is L or maybe small l, whatever, along the entire length of the line, everywhere the same current is tapping, that is I. That is why it is called uniform loading. So the question is, what will be the total voltage drop? What will be the total voltage drop? And what will be the total power loss? That is our concern. So in order to do that, let us assume a small section of length small section of length dx. So this total current feeding at this supply point, it should be I into L. That is the total supply current, because if along the length of the L the current is tapping I, okay, so this I essentially having unit ampere per meter. So essentially the total current becomes I into L. So now up to this length dx length is situated at a length x. So let us say this length is dx. So essentially this current tapping should be I into x. So total current supply, total current fed, that is I into L, and total current tap, it becomes I into x up to point, let us say P. Let us say this point is P. So therefore voltage drop in the section dx, that will be equal to IL minus IX, that is the current, into R into dx. That will be the expression. That is the current, this is should be I into x, IL minus IX into R into dx. So what will be the voltage drop up to point P, VAP? So you should integrate from x, from 0 to x, IL minus IX into R dx. So let us evaluate one by one. So the first term will yield I L R dx. If you integrate with from 0 to x, it will give you one result. Another term is I into R x dx. Now if you integrate, it will give you another result. So if you calculate the first term, it will give you I L R x, and the second term it will give you I into R x square by 2. So this is the voltage drop up to section AP. This is the expression V AP. So in short, if we write, you can write it is I into R. If you take common, if you take I into R common, then it should be L into X minus X square by 2. This is my expression. Now, if you put, let us put X equal to L. So we get VAP is equal to VAB. That means X equal to L means what? X equal to L means it represents the entire length. X equal to L means it represents the entire length. So potential drop for the entire length, which is AB, which is AB. So just put so I into R. Now L into L, X you put L. Now that is L square by 2. So it will be half I into R into L square. So it will be in this way. You should take I into L and R into L. By 2. It's not the small l, it is the capital L. So now what is I into L? So VAB essentially is given by, so it is IL is that supply current. So let us say it is IS supplied. That multiplied R into L, what is that? It is the R of feeder. That divided by 2. So the voltage drop along the length of the feeder, the total voltage drop along the length of the feeder is given by this expression, and that is the product of the total supply current into the total resistance of the conductor, that means feeder, divided by 2. That is the expression. Now, what will be the power loss then? So, power loss can be evaluated as P. So what is the formula? It will be I square into R. Power is I square into R. So that is we going to evaluate. So it will be total power loss. So it starts with 0 to capital L because it represents the entire length of the line. The current should be I into L minus X up to this point P. Okay, up to this point P. This expression. So now it is, since it is a square, so you should take I square into L minus X whole square. Now with that you need to incorporate this term R dx. So you should integrate from 0 to L I square, L square plus X square minus 2 into X into L into R dx. So if you take I square into r common, so you will have an integration. Now this term you will give L square x. The second term you will give it x cube by 3, and the last term 2 into L. Now x dx integration x square by 2. So if you put your limit, so finally you will get I square into r, that will be L cube. Second term will be L cube by 3, and the third term will be again L cube. So it will be 1/3 I square r into L cube. So this should be written 1/3 into I into L whole square into r into L. So the total power loss is given by total power loss is equal to 1/3 into, now IL means this term I supplied. Okay, IL means the total supply current, I supplied square, and RL means this the total resistance of the feeder. So this should be the expression of the total power loss. It is the 1/3 of I square, that means the supply current square, multiplied with the resistance of the feeder. Now with this we have one problem to show you. Let us solve a problem. It is said that a DC two-way distributor, 200 meter long. So in this case capital L is 200 meter, is uniformly loaded with a rate of 2 ampere per meter. So your current should be 2 ampere per meter. Is fed at one end. The resistance of each conductor is 0.3 ohm per meter. So R is 0.3 ohm per meter. What is the voltage drop up to a distance of 150 meters? So that means you can say this is X, or this is the point P. This is the point P. So you can consider your X as 150 meter from the starting point. So this is the point P as per this diagram. So in this problem, this entire length is say 200 meter and this X is say 150 meter. So now we should write the expression. What is Vp? It is written in this way. Is exactly this expression. Now what we are going to write? It should be IR, I into R, then L into X minus X square by 2. Let me check. Yes, that this is the exact expression. So one by one we should enter the data. So I is equal to 2 ampere per meter. Now what is R? R is equal to 2 into, it is 0.3. Now for the consideration of both the conductor, you must multiply it with the 2. So 0.3 into 10 to the power minus 3. Why? Because it is ohm per kilometer, not meter. Sorry, it is ohm per kilometer. So in order to bring it in ohm per meter, you should multiply it with 10 to the power 3. So this is I, and this is R. Now with this L is now 200, X is 150 minus 150 square by 2. So if you solve this, you will get Vp is equal to 22.5 volt. And the maximum voltage drop, the second part is said it is the maximum voltage drop. Now the maximum voltage drop is at this point. That means if this feeder is AB is long 200 meter, if this is 200 meter long, and if this is the point P from 150 meter from A, now maximum voltage drop is nothing but VAB. So maximum voltage drop is nothing but VAB. Now what is VAB? VAB is given by this expression. VAB is given by this expression. It will be half. That is the supply current. What is supply current? It will be 2 into 200. That must divide by R. That means 2 into 0.3 into 10 to the power minus 3 into 200. So if you solve this, you will get this one as 24 volt. So this is the answer. 1 is this answer and 2 is this answer. So now we have feeding at both ends. We have feeding at both ends. So we may have, we are having two cases, different cases. Let us say at node A, voltage is a VA, and at node B, it is at VB. Now we may have two cases. The case number 1 is VA should be is equal to VB. Let us say we are feeding at the same voltage, and the second case maybe we may feed both ends at unequal voltage, VA not equal to maybe VB. So what are those different cases? So now if VA is equal to VB, if VA is equal to VB, that means if both the voltages are equal, then what will happen? Let us check what will happen. The minimum voltage will occur at just midpoint. The minimum voltage occurs at midpoint. That means at x equal to L by 2, because we are giving at equal voltage. So the maximum voltage drop, that means let us say this midpoint, let us say Vp, let us say this midpoint is P at a distance of L by 2. So then VAP, that should be is equal to VBP. So it will be given by a formula IR by 8. This is the formula. Lastly, now let us consider the second case. Now let us consider the second case. If VA is not equal to VB, if VA is not equal to VB, then what will happen? Now minimum voltage occurs not at exact midpoint, not at exact midpoint. Okay, not at exact midpoint by or where it will occur at some distance x, at some distance x. So if this is the feeder, if this is the feeder, let us say this is A, this is point A, and let us say this is point B. We are feeding at both ends. So at several points, same current are tapped out, I. So VA should not be equal to VB. So now let us consider minimum voltage that comes at this point. Minimum voltage, now this is the point P. It is not the midpoint. So where should be the location of P? It should be located x from point A, or it should be located L minus x distance from B. L minus x distance from B. Okay. So what will be V? So let us say this point is P. So what will be VP? What will be VP? Now VP, that should be is equal to VA minus VAP. Okay, VA minus VAP. So what will be VA? VA is equal to VA. Now what will be VAP? VAP is nothing but I into R into x square by 2. From where this expression is getting? It is exactly, you know, this expression. Is exactly this expression. Similarly, if we compare VP with respect, or if you calculate VP with respect to this side, so it would be VB minus VBP. So VB is VBB, but VBP is nothing but I into R. Now x now becomes L minus x. X becomes now L minus x. So if you equate these two, so VA minus VAP, that will be equal to VB minus VBP. So we can directly formulate VA minus VB, which is the drop, VAB, which is equal to VBP minus VAP. So now let us solve. So it will be I into R by 2. If you take common, then the first term is L minus X whole square minus X square. So it will be just if you solve from here, you will get X is equal to, L by 2 plus VAB divided by I into R into L. So this is the expression, or this is the location of X. So even if for the uniform loading, if the both end voltage are at not equal, so the point of minimum potential can be found out by this expression. Point of minimum potential can be found out by this equation. So in this C equation, everything is known. What is VAB? VAB is the drop. What is I? I is the current, load. R is the resistance. Everything is known. L is the total length of the feeder. So everything here is known. So from this expression, we can evaluate the exact location of the minimum potential if both voltages are not at equal level. So VA not equal to VB. So in this part we have studied uniformly loading mainly. So we have seen uniform loading at one end feeding, uniform loading at both end feedings, and for both the cases we have seen some numerical problems. So for this part we shall conclude here, and we shall be showing one more example on DC distribution exciting with AC input. Okay, so in the next section of this lecture we shall demonstrate one problem, briefly demonstrate the problem or radial feeder with AC excitation. So till now, thank you.